Okay.
And oh, okay, they have like a handy. Oh, it started the recording. That's how it
Cool.
works. Okay.
Hi, everyone. Welcome to the recording.
All right. I guess we'll just wait for people to trickle in now, and yeah.
Can you see the chat window that I opened up if I open it up?
The chat window that you opened up.
Yeah.
I don't see anything apart from your slides right now. So
Okay, good. So if I do want to have that, I'm just going to have this up in the corner of my screen. In case.
okay.
And then I have my whole screen shared, right? Like you see my terminal jumping to the front and stuff, right?
Yeah. Oh, we got someone in here. Yeah, one person.
Hi, Tony.
Hello.
Welcome. Oh, shoot. Now I've said someone's name on the recording. I'll stop doing that.
Yeah, maybe. Yeah. Try to.
You'd think I'd learn after a year of teaching remotely.
Oh. I don't know.
I think the easiest thing is to click next to the microphone and click leave computer audio, and it just disconnects your audio from that Zoom session. Whoops.
That does make sense.
Oh, good. The chat is on. That message says to panelists and attendees. Good. That's actually in some sense better for the style of presentation I do.
Okay. Got it. Oh, so you can send it to. Oh, yeah. There you go. Okay.
I think you can lock that down if you want, but I don't think you need to.
Okay. Yeah. No need. Yeah. Should be fine. Yeah. More people. That's awesome. I'm realizing now that we don't really have a place to like show the check-in code. I guess I can post it in the chat when we get started. Yeah.
Check-in code?
Oh, so I don't know if anyone's told you this, but we have an online portal, and then
oh, it's to hook it up to that. No, I know about the portal. I see the mechanics now. I see.
Okay.
Yeah.
All right.
Yeah.
Cool. Yeah, more people.
Oops. Whoa.
Mm-hmm.
Hello to people coming in. The chat is open too. Here, I'll say hi in chat.
Yeah. I'm gonna say we'll get started in maybe like 2 minutes.
Sounds good.
All right.
Ooh, a bunch of people just signed on right after you said give it 2 minutes. So good,
Yeah,
good
wow.
idea.
What I'm realizing I should probably have done is pause the recording until we actually start. I'll do that now. That's fair. I wish I got that last part.
Right.
Darn it. Oh well. Welcome to everyone who just joined. We'll be getting started in about a minute or so. Wait, never mind. It is 4:05 p.m. Okay. I guess we can get started then. Cool.
Yeah.
Yeah. All right. Welcome everyone. Today I am joined by our advisor Joe Politz, and yeah, he'll be welcome to programming language design, and we'll be talking about insert title. So the check-in code for today I will put in chat.
That's the checking code.
That's the checking code.
When you made that, did you realize you were going to have to show me that?
No, I don't make the check-in codes actually. So you can blame our events team for that, but but anyway, you have the floor, Joe. So yeah, I'll hand it off to you, and I'll be monitoring the chat and asking you questions if anyone has any. So take it away.
Yeah, and I managed to get the chat in a reasonable spot here, so I will ask some stuff in the next couple minutes, and over the course of this that I sort of want responses back in chat, and like it's all set up to be open, so you could chat just to us, but I think for the sake of this, if you just stick your chat on panelists and attendees, if I ask for feedback or ideas, it's nice for everyone to see it. So the thing I'm going to talk about is programming language design, and I'm going to do it in the context of teaching computer science. There's lots of contexts I could talk about programming language design in, and I'm happy to sort of broaden this out and take all kinds of questions and try all kinds of things. As I said to Kyle when I was sort of thinking about what we'd talk about, I realized that no one really needs another 20-minute Zoom slideshow. So I'm gonna minimize the number of slides that I present just to have a couple things up, and then I want to drive this a little bit with your feedback, and also some stuff that I think is cool to show, might be cool to show live. So I want to start with this question that I have on the screen now. So the question is, say someone walks into your office, or up to you in lab, and says, I want to teach computer science. You're the expert, you're a let's say a upperclassman in computer science, or even you're a CS major, or you've taken some CS courses. I want to teach some computer science, let's say like at a high school or a middle school, after school. You're the expert. What should I do? How do you answer that? How should you answer that question? I'm really interested in hearing some responses to how you answer that question. I want to teach computer science. You have some expertise in this. What do I do? How do I go about doing that? Okay. Good high level goal. Nice. Other ideas. Anish said, approachable to new people, but cover enough fundamentals. There's a couple of these came in privately to panelists, but okay. Over basics like loops, variable types. Awesome. What else? What else? Someone says get some practice teaching first. You got to start somewhere, right? What else? What else? What else? This is an interesting comment. I'm going to reflect this one back up publicly. It just came to us. Right. Depends on whether you want to teach introductory computer science concept versus inspiring interest in computer science. Yeah, this is an interesting question because it's the first one. It's the first response I got, and if I'd given you more time, you'd come back with more responses like this. But I'll cut it off in the interest of time. It's the first response that came back and sort of came back with an implicit question, like, "Hey, wait, what are you trying to teach?" Because I bet you all would have a very different answer to this question. Like, hey, I want to make some software. You're the expert. What should I do? What's your response? What would your response be to this question? That was from a private chat with panelists. Depends on what you want to make, what kind of software. Yeah, like when I say this to you, right, with even a couple courses worth of programming background, you can come back to me and say, wait, which software? Because my answer is going to be very different depending on if you are looking to write a mobile app, if you're looking to write some data processing program. Like there's a lot of things software could mean here. So let's break this down a little bit more. In the same way, I think that kind of response is a pretty healthy response to the first question, which is like, whoa, wait a minute. Computer science is a lot. Like, which computer science do you want to teach? Who do you want to teach it to, right? And what do they need to know? What's their background? There's actually a lot of like constraints and different things you might need to answer in order to actually sort of successfully pick a programming language and an environment and a curriculum that's going to work for a particular group of students. The same way you'd have to pick a programming language and an IDE and know your users and understand what your goals are in order to build a program. And so this question, I think a lot of times you will, you can say so in chat, right? How many times have you ever heard people say things like, oh, this programming language is better than this programming language for teaching people to program? How many people, like, just say yes in the chat. You've heard someone say, this language is better than this other language for teaching people to program. And probably it was everyone saying that C is much better than Python, right? Haha, sorry. Opposite of that is usually what people say. And so I think that's when people say that, they have a specific kind of audience in mind. A lot of times they're thinking about maybe the class they took, right? Like CSE 8A or 11, right? And they're thinking about what worked in that context and what would be good for, what would be a good fit for that context for those students in that background. So what I want to do a little bit is talk about this programming language I work on called Pyret, and talk about why we made certain design decisions in the context of a very specific audience. Okay? And so there's many reasons we might choose a particular language for a particular context. I want to talk about how we designed a language for a particular context. Okay? So some design decisions and why they work out well in a particular context that we chose. So I am going to talk a little, whoa, I'm actually going to present this slideshow instead of just lingering on it. This one has some stuff I want to talk about. So Pyret has sort of two main audiences. One audience for Pyret is undergraduates. So there's a few intro courses that use Pyret. One is very data science focused, and the others are more data structures focused. And that the data structures course is actually kind of more like a CS2 than a CS1. So think data science-y stuff and data structures. But there's another sort of, actually the biggest audience for Pyret is middle school and high school students in non-CS classes. So there's a collection of curricula we work on called, it's called Bootstrap. So you can look up, it's the URL for this if you're interested in looking it up is bootstrapworld.org. It is not the CSS framework. It's a middle and high school set of middle and high school curricula that do programming in non-programming classes. And the idea here is to reach lots of students with programming who might not take CS as an elective, and to make it easier for schools to fit things into their curricula. There's a lot you could say about the outreach effort there, but that's sort of background to the language design stuff that I want to talk about today. And so as a result of that focus for our audience is like, you can think a little bit about the context of our users and where we're sitting. So, this is definitely not college students yet, although it's, students who might be in APCS classes, but it's also students who are going to be in totally non-CS contexts. And another audience for us, because of this environment, is teachers. So the picture on the right is a workshop where we were teaching physics teachers how to program so they could use programming in their ninth grade physics classes. Okay, so all the people in that picture or most of the people in that picture are ninth grade physics teachers learning to program. And they're doing that so that they can take the curriculum back to their class and do programming in their physics class. And they're learning to program in Pyret, and our claim is that this is a good language and a good context for doing this. So what does it mean? Like what kinds of decisions do we make in order to do this? And so I have a couple like specific examples I want to give where when I'm thinking about language design, a lot of times what I'm thinking about is like sitting over these teachers' shoulders and looking at like their WTFs per minute with programming and seeing, like, that's a technical term for those of you who didn't catch the acronym, WTFs per minute. That's a very technical term. For like where they see that things just like are totally useless to them as like a math teacher or an algebra teacher or something like that. Okay. So here's this, I'm gonna go to a specific example here. So let's imagine, let's just talk about one of the simplest features in a programming language. Like there's no programming language that doesn't have numbers in it that's reasonably pragmatic. So numbers are going to be in the programming language. And so let's imagine for a minute that these are actually high school algebra teachers for a second. So just using these were actually physics teachers, but using this as an example of my train of thought thinking about the language. Let's imagine these are high school algebra teachers. And they're writing a program, they're playing around with the number system, doing some arithmetic. Let's imagine we had, they ran into a situation like this. So take a minute and just look at these examples. Now look familiar at all? Like what is there a programming language that would give you those answers for those arithmetic expressions? Yeah, Python 3 actually would give a better answer for 1 divided by 3, but Python before version 3 just said 0. The second example is a lot of languages will give that answer. Java would give that answer too, for example, because of floating point errors. And if you've taken a couple programming classes, you may not have seen a lot of the details of floating point yet, but once you get up to like CSE 30 and things like that, you learn some of the gory details of how floating point works. But back up. These are high school algebra teachers. They haven't taken any programming courses. Their students may never take a programming course and definitely haven't taken a programming course before this one. And their students are interested in learning algebra concepts and like maybe seeing how programming can be interesting and help with that. Not learning about floating point, right? If an algebra teacher has to get up in front of their class on day 1 and say, okay, 1 divided by 3 is 1/3, except when it's in the computer and then it's 0, they are like really in trouble with their algebra students. Like this is not going to work well, right? And the students are going to have all kinds of misconceptions about what computer math is versus real math. Like this is like a lot to put people through, right? And so some versions of things we've taught with, we run into this problem and teachers are like, what are you talking about? This is ridiculous. I can't tell my math students that 0.1 plus 0.2 plus 0.3 is not 0.6. That would undermine all of my mathematics learning outcomes. So here's what Pyret does on these examples. So this is actually what happens if you go into the Pyret programming environment and type in 1 divided by 3 and type in this arithmetic example. And you'll notice there's an overbar over the 3 and 0.3 to indicate that it's 0.3 repeating. And if you click on it, you get the representation that sort of flips back and forth between a decimal and a rational representation of the number. Okay. When we show this to math teachers in a workshop, they say, oh, this is really cool. Your programming environment is another way for me to reinforce things that I care about, teaching my students about fractions. So this choice, this required engineering work in Pyret. We implemented a library that does exact rational arithmetic and big nums. And I say implemented, actually, someone on the team who wasn't me implemented it, so don't give me the credit for this, but someone on the team implemented this library that does this. And so we've turned a potential pain point in learning for teachers and students in this context to something that's actually like helping them with the learning outcomes they have related to math. So that's a programming language design decision for a very specific context that actually has a lot of payoff, because you do this in like the first half hour of a workshop and you have to build trust with these teachers that you're doing something reasonable in that first half hour. And this is a way to win that trust, and it actually is a real thing that matters. Okay. So this is just numbers, but I claim that this is actually a pretty impactful design decision that we've made. All right, and actually the responses we get are more like, oh, this is going to help. Okay. So this is the kind of trade-off between traditional programming languages you might do and what we've chosen to do. And we're not the only language. Pyret's not the only programming language in the world with exact rational arithmetic. There's others. Okay. And there's some other decisions we've made that are kind of interesting too. So here's another design decision we've made that you might find kind of interesting. I want to take a minute for you to just read this error message. So another thing that comes up in math class is, and even through 9th, 10th grade, I mean, it's taught earlier than that in the US, but even through 9th, 10th grade, students are learning about and struggling with order of operations, right? And there's like acronyms they learn, like depending on if you went to like American middle school, you may have heard of PEMDAS, which stands for parentheses, exponentiation, multiplication, division is addition, subtraction. And so like this is something that students are working on. Now, we actually talked about this with teachers while we were deciding what to do here. And there's a lot of things that teachers don't necessarily want students to only get through like just typing something in and having it work. And like a lot of teachers we've talked to say like, oh, well, you know, I teach order of operations this way, I teach order of operations this way, but everyone agrees that parentheses are a great tool for disambiguating what you mean in an arithmetic expression. Like no math teacher disagrees that parentheses work for disambiguating what you mean. And so we made this decision to force the programmer to do parenthesization of these expressions, so that every Pyret program doesn't need you to understand order of operations until you to read the program. And in fact, it gives you this feedback and says, Pyret's not going to do order of operations for you. We need you to insert the parentheses to make that clear. This also comes with a better payoff because later on, when you learn more programming stuff, and you learn like and or and other operators that have different precedents, you don't have to memorize more and more and more precedence rules. The rule is always just you use parentheses to disambiguate if there's multiple different operators. So this is a decision we've made. And again, math teachers say this is sort of a payoff in the classroom because now the language is supporting their goals of making students aware of and be able to express order of operations. Okay. So this is another design decision we made that sort of in conjunction with teachers that I think has been somewhat effective. Here's another error message. I want to give you a second to read that. So here's another math context thing where in many programming languages, including Python, if you wrote x equals 10 and then x equals x plus 1, both of those would be sort of like assignment statements, right? And the value of x would be 11 after the second statement evaluated. But in math, if I just like go to my whiteboard in a math class and write x equals 10 and x equals x plus 1, right? That is not visible at all, but I did it on my whiteboard. Okay, there we go. And write that on a whiteboard. That's like an unsolvable system of equations, right? If like I do substitution, I've proved that 10 is equal to 11 or something like that. Like there's no value of x that solves these two equations. So that would be weird in a math class. So we made the decision in Pyret, and we also think this pays off for introductory programming too, to not allow this particular pattern. So you can't just like have multiple definitions for the same name. You have to use different syntax if you want to have a variable that updates from just declaring like a local variable that has a temporary value. So another trade-off, another thing that's related to this math context. This one's kind of interesting. I'm not going to dwell on that too much, actually, just for time. But the overall point I want to make here is that we've made some decisions about what people are going to run into when they explore things early, and like put a lot of effort into these error messages and sort of design decisions about what an error is, to help teachers out early on early on for this specific context. We actually think that these pay off for undergraduates as well because they make programs more unambiguous in a few different useful ways. But specifically in the math context, that's what we've been designing for. So I want to pause here. I mean, we're sort of like 4 minutes and 26 seconds, and there's more sort of examples I can talk through and things like that. But I want to see how folks are doing in the audience, if they have questions so far. I also want to know if there's other particular kinds of features you want to that you might have been thinking of coming into this thing that you want to hear about. This is sort of a little sampling to give you an idea of some of the things I think about, even at the very basic level of making design decisions here. So I'm just going to pause, let people ask questions or ask about other things they might want to hear about. I'm not going to like answer them one at a time. I want to like collect some feedback and then decide where to go next. You can also say same if if everyone's really interested in Anisha's question now that they saw it. Good question, William. Oh, I just said who's asking this question. Sorry, I can't see sometimes if these are public. I'm going to reflect this question out publicly. Okay, other questions, thoughts? Okay, so I might go for a. Okay, yeah, I'm gonna program a little bit to answer, because I think the underlying this question about variables is sort of a question about how certain kinds of programs would get written. And so I wanted to sort of work through an example that I think will help answer that. I may or may not say much about classes and objects. I mean, I think the basic answer is that classes and objects in Pyret are pretty boring. I don't think that we made any interesting design decisions about classes and objects. They're quite boring. That's what I'll say. Yeah, so let me go through more of an example. I think that'll be helpful and might spur questions along the lines that like Nishant just asked, and might get at the question about variables and how they update. Okay, so I'm just going to scroll this off the screen. For folks in the audience, can you see my screen okay? Like, should I make the text bigger? It's like this better. Okay. So yeah, I just want to show a little bit of like what the programming environment looks like. So this is the same programming environment I was just talking about, where like fractions look like that. So I've included a library. So one thing that's useful to do with students early on is to work with images. And so I want to show a little bit about like what images look like in Pyret. So I'm going to make a circle. And I type circle, and it's a function of 3 arguments. It takes a number, a string, and a string. And it produces a circle with the given radius and then that number of pixels. And then solid means fill it in. I could also do outline. And red is the color that's being used. And so there's something interesting here already, which is like I typed in circle, and then I like got a circle image, and it like printed right away. Like what is like, that's kind of interesting that I didn't say like make a canvas and draw a circle on the canvas. I just like created a circle, and it draws like a circle. And these images are values in Pyret. And so what do I mean by that? These images are values in Pyret. So I could say like dot is circle 20, let's make it slightly smaller, solid red over here. So the left-hand side is like my program file, and the right-hand side is like where I can interact. So I'm going to run this. And now dot is a variable where I've stored this image. So it's like this image is just a value that can be stored in my program. And the programming environment understands that when it displays an image, it should display it as an image. Like it doesn't display it as like a 2D array of pixel values or something like that. It just shows me the image. Then this is useful because it means I can do things with these images, like in terms of treating them like values. So I'm going to make a background that's going to be a rectangle that's, I guess, 300 wide by 200 high, and it's going to be a black outline. So I have dot, and I have my background. And now I can do things like overlay the dot on the background. Now I get, okay, my ratios are off, but that was an attempt at a Japanese flag. And so we actually have an assignment early on called the flags exercise, where students just out of geometric shapes like rectangles, circles, triangles, and like positioning overlays can create flags. There's another one where they create emojis. And so this is sort of just functions, right? It's all I'm doing here really is calling functions and defining variables. But we made a particular decision about how the image library works, that these images are treated as values that can be composed, instead of like different other image libraries where you might like create a canvas and say, draw on the canvas, and now the canvas is different. This instead is saying there's multiple images floating around here, and I can compose them in different ways. So this already, like, there's no mutable variables here. There were no method calls here. This was just basically creating and composing values, but you're actually able to get to some pretty rich constructions of images here. So this is reflecting a couple design decisions in basically our image library. So let's talk about this other thing I had here. So I had this ball image. I just got a basketball from the web. I downloaded it, and there's a way to import images into here. That has to be easy, but it was easy, so I'm not going to talk too much about how that was done. I actually scaled it. The original image that I downloaded was too big. And let's talk a little bit about how we might do something more complex. So I want to talk about like a physics simulation of the basketball bouncing. This is a problem you might care about in a physics class, like the basketball bouncing over time. So let's talk a little bit about what that might look like. So I'm going to make a different background. It's going to be let's make it a rectangle that's like 100 wide, but like 500 high, and it's going to be outline black. And then a little scene, let's just make sure I understand all the functions I'm using. I'm going to put image, the ball at like 50 for the X value and 450 for the Y value on the background. And let's just make sure all this makes sense. If we look at scene, it's sort of thumbnailed because it's too big. But this is an image where the ball is sort of sitting at the top here because I put it at the X coordinate 50, Y coordinate 450 on top of this background. So this is now my goal is, let's see if we can make an animation of the ball sort of falling down and bouncing back up. And this is a pretty good representative exercise for a lot of the context we care about, but also you could imagine this being a CS1 program. Like, this isn't an unreasonable thing to write in a CS1 class. So there's a couple things that we need to do here. What are some things that you might think we need to do in order to make an animation of the ball falling down and bouncing back up? And you don't have to know anything specific in Pyret to suggest some high-level ideas here. What do we need to do in order to make an animation of the ball falling down and bouncing back up? A lot of you are saying changing the variable, like make a loop and change a variable. So here's an interesting observation. Physics doesn't have mutable variables. Like physics class. Like, think about your physics class. Well, not all of you have taken a physics class. But I want to make this observation. There aren't physics equations that talk about mutable variables, like a variable that just keeps changing. actually the common thing in physics, is that everything is expressed as a function of time. Like in physics, you might say, I want to talk about the height at time t, and that's going to be equal to something. Maybe it's some like initial velocity times something, right? There's some formula here that you'd learn in a physics class. But it's like the height at a given time t is how this ends up being expressed. Right. Physics class doesn't say, oh, the universe runs a while loop, and every time through the while loop, we change these variables. Right? That's not how physics class expresses this stuff, and it's not how a math class would express it. And so we could, there are loops in Pyret that you could use to try and express this very programming, sort of programming specific way, like the default thing we think of after learning loops, right? But if we want to, like, let's say, support math and physics classes where things are written in a slightly different way, now we have an interesting situation. So I'm going to suggest, like, could we somehow like talk about doing this in terms of, let's see, where am I at for time here? I just want to make sure I don't do too long of an example.
Just FYI,
Yeah.
I was planning for this to go until 5, but I think this webinar lasts until 5:30, so
Okay.
plenty of time, I think.
Okay, so let's do the time-based one first. So actually, who remembers enough physics to get the equation here? Let's say I want to represent the ball going in free fall and what its height would be over time. Like, what would the physics stuff be for that? Like, it starts at a particular spot and then it falls with like some normal gravity. We can assume like 1 pixel is 1 meter or something like that. What would be the equation? Like, I want to say the height at time t is equal to something. I want like an equation or a function here. Here we go. Here's a couple suggestions. Yeah, I'm gonna reflect this one out into chat too. So the original, so I'm just gonna try and interpret this last one. The height at time t is the original height. That's how we'll read h0. So let me just copy this. Right. Where t is time, starting at 0. Cool. All right, great. So let's turn this into a Pyret function, because I think that'll be a place to start. So in Pyret, functions are always really fun. So we write fun. That's the keyword for making a function. And most of the block structured forms in Pyret start with a keyword and end with end. So fun end, and this is where we put the implementation of the function. So h0 in our program is 450. That was the y position where I put the ball. And then plus, and we'll say it started at rest. So we have the v0 term kind of goes away. It's going to be 0 times t. Right. Oops. Yeah, and then plus, right? Like, I'll leave it there. I'm leaving, I know we're adding 0, so it doesn't actually have to be there, but I'm leaving it there so we can see the correspondence to the equation. So 450 plus 0 times t, so that would be the initial velocity term. And then we'd have 0.5. And we need a value for g, for gravity. Whoops. 5 times, what's gravity? We need a g. Or negative 9.8, sure. Negative 9.8, just because we'll have it pointing down. Times g times t times t. There we go. Okay, so that's a translation of this formula into a Pyret function. And I want to make sure that this works. And it's always healthy to write test cases for our functions. And Pyret has a really specific way of doing that. And this is actually a nice thing we do to force students to sort of express what they mean by a function when they write it. So what do you think the height will be at when, if I give time 0? What will the height be at time 0? What will height be at time 0? Right? I just made you all think about physics, right? The fact that all of the t terms go away and you're left with just the 450, right? This test case, right? This unit test made you think about something that's physically relevant, right? What about height at 1? Well, it's actually kind of complicated to do the mental arithmetic, right? But we know how to express it as arithmetic. It would be 450 plus 0.5 times g, which we have as a global variable, times 1 times 1. Right? Whatever the result of that is the result. And we could like try and do the right arithmetic in our head to figure this out. This is what, 4.9, so minus 4.9. So we'd expect like 445.1. And actually, that's not bad, right? Now that I've done that arithmetic, I can check if that expectation is right. So I could write 2 test cases. And I can say 445.1 is what I expect that to be. And now I have like 3 test cases. And if all of these test cases pass, like I actually think I might have gotten a physics right here. And notice I haven't done anything with a loop or building an animation yet. I'm sort of just modeling physics as a function. And later in a minute, we're going to get to like attaching the physics to the simulation. But I've gone from sort of the blackboard physics, the physics equation you'd put in the textbook or on the blackboard, turned it into a program that's just a function, expressed some interesting things that you might have written down on paper as a student anyway, right, as part of your exercise in physics class, but now I've expressed them as test cases and I can automatically check them. So let's run the program, see if I've made any typos. It says all the tests pass, so thankfully I didn't make any typos. So this is very Pyret-y themed, all tests passed, mate. So it's telling me that all these passed. If I was really suspicious, I may break one of the tests just to make sure, and it says, yeah, okay, 450 is not 445.1 is not 445, so I did have the right number there. So now what I have is that my program reflects the physics. And by running the program, I've sort of confirmed something about my understanding of the physics. And students do this. So I just want to show you, like, this is not like thing I'm just doing for a demo. This is like a thing students will put on their whiteboard in these physics classes where they're doing like traditional physics class stuff on the left-hand side. And on the right-hand side, they'll be like going through this examples process and doing out some formula from something in class. So this is like how this turns into a class activity. So now we have this thing in terms of height. Cool. Let's attach this to an animation because I sort of like shut down this loop idea at the beginning. Let's see what this looks like to put this into an animation. In Pyret, there's a way to, actually those of you who have worked with any event-based system like Swing in Java or like React, if you've worked on React in JavaScript, the thing we're doing here is actually very similar to these systems where we're going to represent what's going on in the current state of the system, which is a very physics concept, and then how time changes, and then we're going to do drawing in terms of time. So let me first show you a couple of things. So I'm going to write a very simple function called move time forward. I could change what increment I want for how fast I'm going to make time move, but this is just a function that says if I'm at a current point in time and we're going to take one step of our simulation, how far forward is time going to move? So that's going to be the whole state of our simulation is going to be what time is it right now, and the whole way the state updates is going to be by saying, okay, time move forward by 1 step. So that's just a function. That literally adds 1 to its argument. I just gave it a sort of evocative name. But now I'm going to do the part that actually hooks up some of the functions we wrote to an event-based system. So I'm going to have an initial value that time is 0. I'm going to say that when like the event-based system inside the programming language runs, we're going to move time forward. And I'm going to stop there for a second and just show you what we can do with this. So nothing happened, nothing interesting happened. But this R, so I saved this reactor thing in a variable called R. I'm going to type r.interact just to show you something that's happening. Okay. Right now, what it's doing is it's running at some default rate that's built into like the event system actually in the browser, because it's firing some events for time ticking. And every time it's just adding 1, and then it's displaying the value of the current state to me. So what reactors do when you ask to interact with them is they start with an initial value, and then every time this internal timer fires, they call this onTick function, and it updates what's being currently stored there to be the result of this tick function. It's adding 1 every time. Questions about what just showed up on my screen from running those few lines of code? Questions about that? I want to make sure like the mechanism is clear before I go on. And give like a thumbs up or a yes or something in the chat if you're all good with what just happened. Okay. So I'm going to write another function called draw scene. It's going to take a time t. And what draw scene is going to do is it's going to draw the scene at a particular point in time. So I'm going to create an image of the ball on the background at the right place, given what time is specified by the input t. So I'm going to do put image again. So I'm basically building this scene that I had where it was at the top. But instead of 450, I'm going to use the height at that current time. So instead of 450, which was the starting value, I'm going to use the result of our height function at that time. Draw it. And then in a reactor, there's another thing I can do in reactors, which is say, well, instead of just showing that value, I want you to show an image that's the result of calling a drawing function with the current state of the reactor. So I'm going to run this and show what it looks like. Any guesses of like what's going to show up? I want to describe what's going to show up when I hit enter. Let's just see. Oh, it fell. Whoa, really fast. Really quick. Whoa, really quickly. So one thing I can do is I can slow time down, right? So I mentioned that, I was doing like one tick. So one thing I can do with now that I have a program is I can slow time down, right? I can see this happen in slow motion. And that's kind of interesting because now I'm saying I'm doing the simulation at tenths of a second instead of a simulated second instead of a full second per tick, things like that, right? Like this is actually kind of interesting because in a classroom experiment, when you like drop a basketball and would measure how fast it falls or something like that, you can't like slow time down in the physics classroom, but you could model it and slow time down and see what happens if you make this time go slower and slower or faster and faster. Well, kind of an interesting thing we can do. With this to play with it a little bit. But the lesson, like there's actually a few different ways I could go with this, depending on time and questions. We could go a few different ways. But the main lesson I want to give here is that the thing we did is set this up. Really, what the physics teacher cares about is like this stuff. Actually, like this isn't very physically relevant. The function draw scene isn't really relevant for your physics education, except for kind of understanding that if you are plotting something on an XY coordinate plane, like this height is the thing that controls where it's showing up in the up down axis. That's like the physically relevant interpretation of that. But this stuff, right, is sort of the direct translation. G is a constant. This represents the motion in terms of time, and that was like translated from this mathematical operator or this mathematical expression. And then the reactor sort of ties that stuff together. The reactor says, I'm going to run some time ticks, and you're going to tell me how time advances, and you're going to tell me what to draw at every moment in time. And so this decoupled, this makes it so the student never had to learn about while loops. There's no mutable variables here at all, right? But the programming task was writing a function that translated the mathematical expression, and then using this idea of a reactor. Now, it turns out that this idea of a reactor is like how industrial event-based systems work, right? You register event handlers, they change state. It turns out that this is just a pattern from like good software engineering practices. But it also has the benefit that we didn't have to teach anyone a while loop to do this. And this is a lot more, this is just in my experience has been a lot more palatable to teachers than having to learn about like, you know, the stopping condition. Like I didn't even have to talk about a Boolean here, right? Like I didn't have to introduce that entire curricular concept in order to get here. We have other lessons where we introduce Booleans, but we don't have to do Booleans before we do an animation, right? So that kind of thing has is you know, showing a couple of the benefits of sort of carefully setting up the programming environment, the programming language features, and the libraries in a particular way. I'll stop here for questions, and also so we can just check the room, see how people are doing, and if people want to see more or the next thing I would show if I were doing this in sequence, stuff like that. But I'll pause here, take questions. Also, if this example was, you know, confusing, I kind of went fast through it. Feel free to ask questions. Feel free to ask questions about anything about the language too.
I know there were a couple of unanswered. Sorry, I know there were a couple of unanswered questions in the chat earlier. I'll go through those.
Sure.
If you don't mind. Let me pull this up. Okay, so if it's geared towards math/education, then are there major features of a typical programming language that you dropped? Is the question.
Yeah, I wouldn't say that Pyret is missing any features, any like major features, right? Like there's, you know, it doesn't have, I don't know, inheritance, but it's no one who uses it cares. So that's like dropped, but also like not necessarily a part of every programming language. I think for the major things you care about, like being able to make data structures, lists, sets, dictionaries, those kinds of things are all there. Loops are there, like those kinds of things are all in the language. The thing we've done is made some of them a little bit more annoying to get to. So like, if you want to have a mutable variable, you just have to declare that it's a var instead of a, so x's value is currently that. Now x's value is 10, and you use a different syntax for updating it. So that's what mutable variables look like. And, you know, that's fine. You end up teaching that a few weeks later in an undergraduate curriculum, and that's the syntax for it, and you teach it as a separate thing. So I'd say there's some stuff that you might want for advanced features, but most general purpose programming things are in Pyret.
Okay. Other questions, let's see. Do variables have scopes, or are they all just global? I think
so T here is definitely function scoped. So like G is a global, but if I tried to use T, it would say T is unbound because T is only defined inside height, move time forward, and draw scene. R is defined because it was defined in the tuple. So there's pretty explicit and traditional scoping rules.
Someone just asked a question: is Pyret used for education/teaching purpose?
Yeah, mostly. I mean, I think unless you like enjoy pain, I wouldn't use it to write a production application. Mainly for performance reasons. There's a lot of things we do for checking things at runtime to do good error messages that slow things down, but no one, no student cares because their animations run just fine. Like there's no animation that gets slowed down by this stuff. But if you were trying to use it to do like fast data analysis, you'd probably be sad.
Actually, I have a question.
Yeah.
So from what I can tell, I've done a few workshops, as you probably know, about functional programming languages, Haskell specifically. It seems to me that Pyret is functional, which is, well, from what I can tell, Pyret looks like it's functional anyway. You mentioned earlier that Pyret is meant for people who do not code, right? People who've never taken the CS class before.
Yeah, sure. I mean, that is an audience. It's not the only audience, because like there's sort of CS1 data structures-y folks who are pretty happy with Pyret 2, and so I wouldn't ignore them, but definitely an audience is totally fresh programmers.
Got it. Okay. How do I word this? So do you have personally like a preference one over the other? Like I know a lot of like prevalent languages are not functional, like C, Java. They're all like imperative and work like directly with hardware and stuff. So,
And
well,
so
really.
let me say something and see if I'll say a simple sentence and see if this is getting an answer. I think programming in a functional style is good for this audience.
Okay.
And that's actually largely because these classes, like math and physics classes, and also like freshmen, but I less want to say that about like freshman programmers in college, because it's a little less like obvious that that's the context we want to have for them. But like in a physics or a math class, you're talking about functions. Like it is like you don't get through a math class in high school without talking about functions. And the functions in math act like the functions when you're programming in a functional style. So that's the style we use for all of this material. Now, Pyret has mutable variables, mutable data structures, right? All that stuff. And if you look at, the sort of the textbook that we've written to go along with Pyret, you'll see like halfway through it switches to a mutable style to do graph algorithms that need it, right? Like it's really painful to do graph algorithms without mutation. So, Pyret has all those features too. We just organize our curriculum to do functional style first. This is a question to the panelists. Is there anything you would change about Pyret? Yeah. I mean, currently, I really wish, I really wish we didn't, like, this is a silly thing, but I think it matters. I really wish we didn't need the end keywords everywhere. But I really don't want Pyret to be indented. So Pyret has a nice design principle, actually, that it's not like Python where the indentation is not significant. Like I can mess up all the indentation and it's totally fine because of those explicit ends. And you can re-indent the program and there's sort of a canonical formatting for a Pyret program, which is a nice thing. But it relies on these end keywords. And my gosh, like novice programmers miss those end keywords all the time. I feel so bad for them. Like it's just such an easy thing to forget. And so if we could do a syntax design where you didn't have to have explicit ends, I think that would be like a huge improvement to the language. It's like a silly syntax thing, but like seriously in that mode of standing over people's shoulders and watching them like forget an end. And then the error message isn't that good because it's like, where do the ends balance? It thinks that all of this is part of this block. Like those things are like, I wish I could do a better syntactic design for a few cases, and one of them is these end keywords. And I think that'd be relevant for professional programs as well. I mean, no one likes bad syntax errors. Oh, is there any reason to not use braces? Purely marketing. We wanted the language to look more like Python and less like C and Java. So, you know, it would but people have this meme that C and Java are bad for introductory programming, so we would have a harder time selling it. I mean, we don't not selling it. I don't mean that we make money off of it. Selling, I mean like marketing it and getting anyone to use it, because they would be like, oh, C and Java are too hard. It has to look like Python. Somehow Python block syntax is easier. So that's what we did, all marketing. Even research projects need marketing. Otherwise, you don't have any users. If you took out the end keyword, it would have to depend on the indentation being correct. That would be one way to do it. So you could take out the end keywords and have significant indentation. I have some experiments where I've tried to be like sufficiently clever and figure out, like write a parser that figures this out without the end keywords, because you can kind of tell, like if examples blocks have to have just a sequence of is tests in them, then you would know when you get to the fun keyword that you're not in an examples block anymore. So there's ways to do this unambiguously, but it's a tricky design, and you kind of have to do it from scratch. You can't do it in a backwards compatible way. So the easy thing to do is make indentation matter, but then you run into Python's problems. Like it is a superpower in Pyret that if you have a totally weird like indentation going on in your program, you can always like just highlight everything and press tab, and it's like that's the indentation for your program. It's correct. So in Python, you can't do that because if you move the indentation around, you change the meaning of the program. Cool. Awesome. I see people sort of probably had 5 at the end on their schedule, so I'm happy to take more questions, but I don't think I'll present more today. If you want more language design, just have me back another time and I can sort of pick up where I left off with more advanced stuff.
Yeah, for sure. That'd be great.
Yeah, any other questions? I'm just saying I'm not going to like do more programming right now.
I have a list of questions here about like more general like general knowledge about like the programming language scene in general, I guess. What do you think makes languages successful?
Oh, knowing your audience and spending way more time on like the environment, the programming environments, and like the nice little features than anything else. Because like the amount of work that goes into like for Pyret, the amount of work that goes into like good error messages and like having a web-based environment and all that stuff totally dwarfs the time of like actually thinking about what the syntax should be and implementing it so it works when there's no errors, right? And like if you look at why Rust is doing so well, you know, they are working so hard to make their error messages good, to make their tutorials good, to make like all of the installation and everything so easy, right? Those are where people leave because it's frustrating. So like those things are where success happens, right? Like TypeScript nailed this, and TypeScript was easier to use than Flow.js, and TypeScript is like clearly won over Flow, which was like the JavaScript type system from Facebook that required more installation steps and more work importing code, and TypeScript doesn't. And it like that's definitely why it's not like TypeScript has a better type system design than Flow. They were both super cool, but TypeScript got all of like the little creature comforts down better. So I think that's the main thing. It's having an audience, right? Like you can't just make a language in a vacuum and expect people to come. You have to have an audience of people who care. Like Rust has systems programmers, you know, Swift has iOS developers. TypeScript had, you know, frustrated JavaScript developers, right? They have an audience, but then they really, really work on all the tooling and the pleasant stuff.
Yeah, this is kind of related to another question I'm starting to have. So how does a language get from like just starting out, no one knows about it, to like being the de facto thing that you have to be using for this one application, like JavaScript, for instance. Like it is now kind of the default language for like web development. Yeah.
Yeah, I think they all have different stories. Like Rust is really like Rust didn't have to exist and is really sort of, you know, it's impressive. They're like battling for their adoption in a sense. They're really making the case, right? JavaScript was the right place, right time, right? It just got put into browsers and used, and then backwards compatibility was a problem forever. So it's just been JavaScript forever, right? So that was just there, right? Java was much more Java's like Rust. I mean, Java was made at Sun as basically a giant research project, industrial research project to make a good programming language for applications programming, because for memory safe applications programming, Java's like Rust. You know, I don't know the early history of C and C++, but they are also a bit of like, my sense is that it's more like right place, right time. They were there. So they got ubiquitous on certain systems early. I think other places have captive audiences, like Swift has a captive audience because Apple's producing it for writing Apple programs. Python seems like a little bit more organic growth. Like it didn't really fight for its growth the way Rust does. Like there weren't a lot of people that it was trying to evangelize to. Python seems like one of the more organic stories where they had a friendly community. Like the community was pretty open and friendly, and started being used for education. People started writing a few cool libraries in it that went to C code and to do fast stuff in the background. And then more and more people just jumped on it. But Python has always been pretty easy to install. And then it became default installed on so many operating systems, right? I think one thing I'd say though is like every power of 10 is like this is something someone said to me at a programming conference once. Every power of 10 of users is like a completely different challenge. Like going from 1 user to 10 users is a big deal. Going from 10 users to 100 users is a big deal. Going from 100 users to 1,000 users means you probably don't know all your users anymore, right? Going from 1,000 users to 10,000 users is a big deal because like that means you're spanning like multiple organizations and stuff like that. That's where Pyret's at. Like we have like, you know, 10,000 to 20,000 users a year. I don't know like what it looks like to get to 100,000, right? Because you need a certain other level of just like ubiquity and people discovering it. So I think every level of number of users is a big deal. Different strategies for if you wanted to market it for that.
Yeah, it makes sense. There's a question in chat. What are your thoughts on Wolfram?
I mean, it exists and it's kind of impressive in its domain. Like I think the claims of it being, you know, like I feel like, well, Wolfram's the one where they're like, yeah, it's going to solve every computational problem if you just like think hard enough at it. It's even just going to pick up your brain waves and then solve problems. I think that it's actually really impressive what they've been able to do with natural language stuff in Wolfram. Like you like write down a thing in English and it works. It's really cool. I think that it would be hard to build large software systems in Wolfram because of the ambiguity and the fact that it, you know, kind of references data that might change over time, and it has these databases backing it. So it's more like an end user programming language than something you'd build large systems in, which is an interesting contrast.
On the topic of weird languages, I also taught a workshop with another ACN guy on APL, if you know what that is.
Yep.
Yeah, very, very interesting language. I don't know. What do I have to say about it? It's, yeah.
I mean, APL is it's just so dense, right? Like all of the operators in APL, you could imagine writing them out as like a Python function or like a Python list comprehension, right? It's just remembering where all the implicit arguments go and in what order.
Yeah, I think
I mean,
it definitely has. Yeah, it definitely has the potential to be really powerful. It's just remembering all the symbols, right? Yeah.
Yeah, I mean, I feel like when I read it, I have to like expand it out to like basically like list comprehensions in my head, and then like evaluate it, and then like think about it that way. That's how I think about it.
I see.
Don't teach Lisp, teach Racket. Mm. Oops, I sent that only to I sent my sick burn only to panelists.
I imagine most of us are unfamiliar with both. So maybe so what does Racket offer that Lisp doesn't? I kind of know on like a really high level what Lisp is, but yeah, I'm curious.
So I think there's a couple things. So I think Racket is a little more, I guess the main thing is that Racket has a much more what's the word I want to use? I think the design of Racket has just such careful design on so many things, like so many things. Like Lisp is like, I don't know, there's some analogy here where Lisp is more like C and Racket is more like something else that's better. Um, like maybe like Racket is more like Rust or something like that in that analogy. Like there's just so many things that have this like careful cohesive design in Racket. Most of them like sort of come with a research paper and like have, but also Racket has enough users and enough like performance measurement and stuff that it's pretty solid for large engineering tasks. It's just a um impressive language, but I'm biased. I mean, my academic like genealogy is all Racket people. Super
I
biased.
see.
I actually have I've written like fewer than 1,000 lines of code in Rust. I would not say that I like even know Rust that well. I sort of just um, know people in the community and admire it from afar. I haven't had a reason to write a lot of code. I mean, it just depends. I mean, I think what are my favorite things? Um, I mean, like ML and Haskell match, right, is like amazing. It's like one of the coolest language features, right? Match. Like
Do you
that's
mean
so
like
awesome.
pattern matching?
Yeah.
Yeah, that is also one of my favorite features.
Um, I think JavaScript has a feature that's not part of the language, but it's part of how it runs. Like the fact that JavaScript and the web page are so intertwined is way different than any other UI programming environment that's gotten mainstream. And I think that's really cool. Like the way JavaScript and the web browser page interact is really cool. So I'll just say like the JS DOM API is really cool. Python has match. I looked at that proposal. It's like really ugly though. This
Yeah, I
one?
remember. I remember Ranjit was talking about this in 130.
Yeah, it's like super ugly, I think. Maybe it got better. Oh, this isn't so bad.
So it is just kind of like it's kind of like a case of kind of like it is in Haskell, but just not.
Yeah, can you do nested matches? I mean, that's the question. Like if we look at this grammar, can we do nested matches? Where's the grammar? The match protocol. Ah, there we go. Case block case pattern. It's a walrus pattern or an or pattern. Walrus pattern is that.
Oh, they actually show you the grammar for the language. I never knew that. It's really cool.
Closed pattern. Yeah, I mean, I think it looks like I think there's not nesting, which is annoying. But yeah, this is cool. I'm glad this is getting in. This is an improvement. Nice. I actually realized I should get going. I didn't realize we were 5:17. So
Okay,
I
well,
probably need to wrap up.
all right, that's fine. Well, thank you for joining us. This was really interesting.
Yeah,
Yeah,
feel free to
if
reach out if you want me to do another thing on any of these languages or other stuff about Pyret. You can be more specific about what you want to. I sort of just guessed at something that would be interesting to talk about. So I'd be happy to do something more specific if you want a particular tutorial or something too.
yeah, that'd be great. Yeah. I don't think I'll be on board next year, but yeah, we'll see. I don't know.
Sure.
But yeah. Maybe Chris has some ideas. I don't know.
Sure.
Yeah, the APL workshop was his idea. So
Sounds great.
all right, well, I'm gonna stop the recording now. Yeah.